So all we have left to do with this example is to actually calculate Kb for the nitrite ion. Well, in order to do that, I am going to quickly switch over to another chart here where I have more space. And I'm going to use the equation we just came up with, which was that Ka times Kb is equal to Kw. Well, we all know that Kw for water, assuming we're at 25 degrees Celsius, is 1 times 10 to the negative 14th. And since Ka for our acid was 4.6 times 10 to the negative 4th, I can fill that in as well. And I'm going to let you guys go ahead and calculate Kb by dividing on both sides. Ready, set, go. All right, and then we can do the same thing for a base. So here is another situation where we have a base, and we're going to try to figure out what is Ka for this acid. So this would be the conjugate acid of aniline, which is our base. So notice C6H5NH2, if we add a hydrogen here, it gives us this right here. So that's going to be the conjugate acid. Now, I'm going to skip all the equations, and I'm just going to remind you guys that Ka times Kb equals Kw. All right? And you are now going to go ahead and fill in the values that you know and solve for Ka. Ready, go. All right, so let's take a look at now a situation where we can look at salts and predict if their solutions are going to be acidic or basic based on looking at Ka and Kb values that you will find on the following pages. In your textbook, they are going to be 658 and 678. So first of all, sodium phosphate. How do we approach it? We would say, well, what's the parent base and acid? Well, sodium, of course, implies that this came from sodium hydroxide, because that's the only acid or base that is going to include sodium. Phosphate, of course, would come from phosphoric acid, H3PO4. We look at these two, we identify their strength. So I'm going to look at this one and say that is a strong base. This is a weak acid. So my base is stronger, so therefore this salt would be basic in solution. I can take a look at the next one. Potassium iodide would come from potassium hydroxide, hydroiodic acid. And I look at both of those and go, hey, that's a strong base and a strong acid. So this one, they basically are going to cancel each other out. And now we would have a neutral salt. All right, and we will say neutral acid, basic salt, even though they're only really acidic or basic in solution. All right, next one, pyridinium chloride. So if you take a look at this one, it's kind of tricky to figure out where the anions separate, but it would be right there. And if we separate that, we go, well, the base that this thing must be coming from is probably going to be that thing, hydroxide, for example. So pyridinium hydroxide, I'm just going to call it POH, not to be confused with POH. Get it? Combining with hydrochloric acid. Well, here I have a strong acid. This right here, pyridinium hydroxide is not on my list of strong bases, so I know that that is a weak base. So in this case, the acid wins. This would be an acidic salt. All right, so those are the three most common situations. But what happens down here in letter D? Just check this out. Here we would have ammonium hydroxide, or you could think of it as ammonia, take your pick, reacting with hydrofluoric acid. Well, now we have two things that are both weak, all right? Both of these are weak. So if I go weak, weak, do they cancel each other out? And the answer is maybe, right? It kind of depends on the relative strengths of them. So how would we figure that out? Well, we would figure that out by looking at their Ka and Kb values. So on page 658, you will see that the Ka for HF is 7.2 times 10 to the negative fourth. And then if you take a look at page 678, you'll see that ammonia has a Kb value of 1.8 times 10 to the negative fifth. So looking at those relative to one another, you will realize that the Ka there for hydrofluoric acid looks to be about 40 times bigger than that of ammonia. So in this case, it's not going to be super acidic or basic. It's going to be a smaller, smaller effect on the pH. But this one would be slightly acidic because even though neither one is strong, in this case, the acid is stronger than the base. So the last step is now to take a look at one of these solutions that contains one of these conjugates of a weak acid or base and see how it affects the pH. So here we're going to calculate the pH of a 0.5 molar sodium nitrite solution. So what's going to happen here is that when this dissolves, it will dissociate completely, as all sodium salts do. So as a result, this is going to give me 0.5 molar nitrite ions in solution. So what's going to happen with those nitrite ions? Well, when I have a nitrite ion in solution with water, because it comes from a weak acid, it's a relatively strong conjugate base. So it likes hydrogen ions. So it's going to steal a hydrogen from the water, forming a molecule of nitrous acid. And of course, a hydroxide is left behind, which is going to affect our pH. So how are we going to go from here? Well, it's now time to do some icing of this problem. So let's talk about what our initial concentrations were. As I mentioned up here, since this dissociates completely, we're starting off with 0.5 molar nitrite ion. Water is a liquid, so we will ignore it. Prior to any dissociation, or in this case hydrolysis occurring, the concentrations of our two product species is 0. We know that we are going to dissociate a little bit, so these guys will both increase by X, this one will decrease by X. And we don't know yet whether this X is negligible because the K value that we have is a Ka value for nitrous acid. We need a Kb value for the nitrite ion. But we just learned very recently that if we have a conjugate acid-base pair, the product of their two equilibrium constants is equal to Kw. So in this case, I know Ka for nitrous acid is 4 times 10 to the negative fourth. That times Kb will be equal to 1 times 10 to the negative 14th. So I divide on both sides, and my answer is 2.5 times 10 to the negative 11th. So that is really, really small. And as a result, I know that this X value over here can be ignored when adding or subtracting it to a non-zero number. So my equilibrium concentrations of these are going to be 0.5 molar still for the nitrite X and X. All right, all we got to do now is come up with our equilibrium expression here. So Kb for this particular nitrite ion in solution is going to look like this. HNO2 concentration times hydroxides divided by the nitrates concentration. And it just so turns out that we know this Kb value now, 2.5 times 10 to the negative 11th. The nitrous acid and hydroxide concentrations are both X. So I'm going to go X times X and just write X squared divided by the nitrite concentration of 0.5. I'm going to multiply by 0.5 on both sides of my equation. I am then going to take the square root of that value. And when I do that, I get an X value, which would be the concentration of hydroxides and nitrous acid, of 3.54 times 10 to the negative 6th molar. And that goes in both of those places. So that is my concentration of hydroxide. So we're only 2 steps away from our answer. The next thing we want to do, since that's hydroxide concentration, we are going to say the pOH in this case is the negative logarithm of 3.54 times 10 to the negative 6th. And when I do that, I get 5.45 as my pOH. And then to calculate my pH, I finally just subtract that one from 14, and I get a pH value of 8.55. And yes, it is basic. All right, I hope that helps. Go back through, rewind when you need to, figure out the details, and then try some practice problems.